Welcome back, everyone. Today we're going to be looking at a circuit, but instead of focusing too much on the audio path, we're actually going to focus on some of the non-audio things that are going on. I wanted to talk today a little bit about synchronized LFO signals in guitar pedals. And the use for synchronized LFOs can be found all over the place. If you think about it, music is a very rhythmic activity, and if you have two different effects going on, you want them to be in time as much as possible, unless you're going for a very specific effect. And using synchronized LFOs is really important if you're trying to do things where you're splitting the signal up, or where you're trying to make sure that multiple bits of circuit are operating in sync with another bit. Because even if you use two identical LFO technologies or topologies with the same value components, because of tolerances and because getting a potentiometer set exactly perfectly is so difficult, you're likely to have some kind of drift going on, and your LFOs will get out of sync and it won't be very musical. There are lots of pedals that use synchronized LFOs. The Dimension chorus is a very popular one. Tri-chorus is another one. And the one we're going to be looking at today is actually the Harmonic Tremolo. The Harmonic Tremolo is an effect that dates back to the early 1960s brown face era Fender amplifiers. And in summary, the way a harmonic tremolo works is you split your signal into high frequencies and low frequencies, and then you apply tremolo to them, but where the LFO on one side is out of phase from the LFO on the other side, and it creates this different effect that creates a lot of interest. And in the old Fender amplifiers, they would sum those signals back together at the output, but some of the more modern implementations will actually allow you to send your high and low frequencies to your separate left and right outputs, so that in stereo you get kind of this additional effect going on. At its core, the harmonic tremolo is really pretty simple. The circuit we're looking at today is the build your own clone version of the brown face tremolo, just because it's pretty easy to understand from a building block standpoint. There are others like the Earthquaker Devices Nightwire, or the Cardinal Harmonic Tremolo, but those are a little more complex. We're not going to look at those ones today. So if we were to break our circuit down here a little bit, we've got our input stage, we have a filtering stage, we have two identical transistor stages, and we have the output stage. This is our audio signal path right through here. Okay, everything down here is all non-audio related, and it has to deal with our LFO. So let's go ahead and take a look at the audio signal path first, because it's pretty simple. So if we start by looking at this input transistor stage, we recognize that we have a pull-down resistor, we have a DC blocking capacitor, we have a transistor where the collector is tied directly to power, and we have a resistor on the emitter to ground, and we're taking the signal off the emitter. This is a unity gain emitter follower stage. Okay, remember that if we take the signal off of the emitter, it's going to be in phase and unity gain compared to what is on the base here. So that's always kind of the big giveaway, is if we're pulling the signal off the emitter, it's going to be in phase, and we can never get more than unity gain out of this. Okay, so this is just acting as a buffer where we get a higher input impedance and a lower output impedance. You'll notice that we have this 1 megohm resistor that is connected to the base of the transistor as well. If we follow that down here, it comes to a bias voltage potentiometer. So this right here is our bias resistor. This is providing the bias voltage that our audio signal is going to ride on, so that the transistor can produce both the positive and negative voltage swings. If we didn't have this, it wouldn't work. Remember, biasing. It's important in electronics to always be biased. Okay, so that is our input transistor stage. Pretty simple, right? Next, we take our signal out, we go through a resistor, and then you'll see that we have two parallel RC filters here. We go through a cap and a resistor to ground, which makes this a high-pass filter. We then go through a cap and a capacitor to ground, and this is a low-pass filter. And you'll notice that our resistors and our capacitors are the same value. What this does then is it splits our signal up into high and low frequencies. And because we've chosen the same value capacitors and resistors here, we have put the 3 dB down point of these filters at the same place. And if you remember, if we take a high pass and low pass filter where their 3 dB down points match, and we end up summing these responses back together, we get a nice flat response. Now, it won't be perfectly flat. There'll be some very small variations, but for all intents and purposes, you sum the output of these two together and you get a nice flat signal, which is exactly what's going to happen out over here. Is we're going to sum those signals back together. But because we want to process the high and low frequencies separately, we've split them up this way. Okay, so we've got those RC filters that are splitting up our signal into high and low frequencies. After that, they each go through an identical transistor stage. And the transistor stage looks like this. Okay, this is actually pretty basic. We have a DC blocking capacitor here. We have our signal coming in on the base. We have a resistor off the emitter to ground, and we have these resistors from power to the collector up here, which means that we are setting this up for some amplification. And we've got this resistor coming across. This is providing some bias for us. And it's also acting as a large negative feedback resistor because the signal off the collector is out of phase. And so all we're really doing here is we are taking advantage of the fact that we can have a high input impedance and a little bit of gain here after a passive filter. Whenever you do something that is passive, these passive components are going to typically tend to have a higher output impedance. And so you want to make sure that you've got something with a high enough input impedance that you're not actually losing any signal across here, which is exactly what happens with guitars. They're passive. The pickups and the electronics on board are passive components. They have a high output impedance, and so we need a high input impedance to prevent any kind of loss downstream. Okay, so pretty basic transistor stage there. And on the output of this transistor stage, we see that we have a big DC blocking capacitor, and then we come into this output stage here. This output stage is a simple summing amplifier. Okay, we're using the base of our transistor and the output on the collector to sum our high and low passed and modulated signals back together. 9 volts through a resistor, and then a resistor to ground is setting the bias on the base of our transistor here. And then we have a resistor from emitter to ground, resistor from power to our collector, which means we're setting this up for some amplification. We get a phase inversion right here because we're coming off the collector, DC blocking cap right there, and then we have a level control at the output, which is also serving the function as a pull down resistor because from here, it's always seeing a constant 100K to ground. So pretty simple transistor setup here as well. So we see that the audio path is really not all that complicated once we start breaking it down. Now, to get into the slightly more interesting part of this circuit, we're going to take a look at the LFO. And we're going to divide the LFO section into two different pieces. The actual waveform generation happens here. And then what we end up doing with it so that we have two synchronized versions happens here. Okay, so we're going to take a look here and then we'll walk through here. So first is the actual LFO generation. We're providing 9 volts through an LED and through a resistor down onto the collector of this transistor. And this transistor happens to also have a path through this 2 meg 2 resistor to the base of the transistor. But the base of the transistor also sees a network of caps and resistors. Okay? In fact, if we take a look at this, our emitter's just tied to ground over here. And we have this path between the collector and the base, but we also have all of these things between the collector and the base, and so that means these are all in the negative feedback loop of this transistor. So what ends up happening is that we have power, we have voltage that's coming down through our resistor, and as it comes down through the resistor, we start charging up these capacitors. As we charge up these capacitors are going to discharge whenever there is a charge differential across them. And these resistors here, as well as the transistor itself, are providing paths for these capacitors to charge and discharge. And what happens as those capacitors charge and discharge is that they begin to actually turn this transistor on and off more or less depending on the voltage that gets onto our base here. And so we have a fixed DC voltage that's going to be on our base to bias the transistor, but then these caps and resistors, as they're charging and discharging, are causing the voltage here to fluctuate, which is going to turn this transistor on and off more or less. And so that is going to create a time varying voltage out on our collector here. And the output of the collector is where we take the LFO. All right. So the way that we control how fast that happens is between the combination of the capacitor values and the resistor values. So every RC circuit has a time constant that is the charging time or discharging time. It determines both. And so if we have a fixed resistor here and all of these are fixed caps, then we can actually change the time with one variable resistor here. Because as we turn the speed potentiometer up, we create a short to ground here, which means that the only resistance along this leg is going to be our 1.8K resistor. And when it's only a 1.8K resistor, it can start dumping the charge down to ground more effectively. But as we turn the speed pot down, this resistance goes up, which means that it's providing much more resistance to this charge, so it's going to discharge more slowly. So this topology here, if we were to rearrange it a little bit, you would recognize this from our earlier video on the regular full band transistor tremolo. It also gets used in the Univibe. It's called a phase shift oscillator. Okay? And so once we've got that LFO signal right here, We go through a DC blocking cap to make sure that we don't have any DC voltage coming out. And then we go through this resistor and cap to ground. This provides a low pass filter at a really low corner frequency because our LFO is going to top out at something around 10 hertz, about an octave below the audio range. And so we don't need any kind of audio signal which may be present due to noise or whatever else. So we're just going to filter that out here. And then we've got another DC blocking cap. We have this 1 meg resistor that's providing the bias onto this transistor. And then this transistor and 2 resistors and 2 capacitors is performing a very specific and important function. The section there in that box is what is called a phase splitter. It takes a signal in and it splits it into equal but out of phase components out. We've talked about how if we have a signal coming in on the base, the collector is going to be out of phase and the emitter is going to be in phase. And when we set the emitter resistor and the collector resistor to be identical, that means that we are setting them both up to have the same amount of amplification, which is going to be unity. Okay, so we put our LFO signal in on the base. We have these equal resistors, which set up our transistor for having our, if we have a positive swinging LFO coming in on the base, up here we'll have a negative swinging LFO, and down here we'll have a positive swinging LFO, but these two LFO signals will be perfectly synchronized but out of phase. Okay, that perfect synchronization is really important to us because we want to be affecting our high and low frequency components up in the audio path at the same time and in the same way. So the output from the phase splitter there goes into 2 identical transistor stages, which are these. Okay, now this transistor stage is just using this transistor as a variable resistor to ground. What that means is that as we get a higher voltage on the base, the transistor turns on more, which means it's a lower resistance to ground, which means that our signal up here is going to see a lower impedance path to ground by going through here than it is by going through our transistor. So large voltage here means that we are dumping our signal here, which is the dip in the amplitude of our signal that is characteristic of tremolo. But you may ask, how do we control the depth of that? The depth of that is being controlled by this potentiometer right here. I'm actually going to get rid of that box so that we can see it a little better. Just like our transistor stage over here, we are biasing this transistor by way of this resistor here, but now we have 2 resistors in parallel to ground. And so the bias voltage that's going to be on our transistor is going to depend on the parallel combination of these 2 resistances. And so this is a fixed resistor, right? And there's a fixed resistor here to make it so that we don't completely starve the base of the transistor. But then we have this depth potentiometer. And this depth potentiometer is going to raise and lower the bias voltage on the base of our transistor because it's changing the ratio of this resistance to this resistance, which is a voltage divider. Okay, so as we change our depth knob, we are taking the bias on our transistor and we're raising it up and down, which means we're pushing it either further into turning on this transistor more, or we're resulting in having it be more starved so that this transistor is not turned on as much, so that the range of resistances this can provide is higher with a lower voltage here. Okay, so as we turn the depth pot up, we see more resistance here, which means overall we see a higher bias voltage, which means we're turning this transistor on more. at an equilibrium state, which means that whenever we put our LFO signal on here, it's going to cause this to be less effective resistance and therefore reduce our signal more. Okay? If we were to completely starve this of voltage, this transistor would never turn on, and we would never be dumping any signal through here, and we would just hear a non-modulated signal on the output. And the exact same setup is used down here for the other phase of the LFO, and these two potentiometers are actually a dual gang potentiometer, because you want the depth of both of these to vary the same at the same time. Okay? But other than that, this bottom part, this top part, they are identical, which means that they are both dumping off signal at the same amount, but out of phase between the high and low frequency components, which is what the harmonic tremolo signal is. So there we go. Just a brief recap. We have a buffer. We have some RC filters to split the signals into high and low bands. We have a transistor gain stage. We have a summing amplifier to the output. But before we come into this gain stage, we have a variable resistance to ground that can dump our signal off depending on how strong the LFO signal is here, which got generated back here. Okay? Lots of squiggles, lots of boxes, but if we take our time to break the circuit down into its component parts, we see that it's actually just a combination of several very basic components, which is what most circuits are. And when you design your own circuit, start from things you know. I don't necessarily recommend just changing one or two components of a known circuit, but rather take bits and pieces from one and from another and combine them. Use the building blocks to make something that is really your own, instead of just tweaking a couple of values and leaving the topology the same. That's where you start getting into these effects that are really unique and special and can really be yours. I hope you found the video useful. If you have not subscribed yet, I encourage you to do so that you're notified when the next one comes. But until then, thanks for watching. We'll see you next time.